Our second speaker is Julia Ziegler. Julia did her bachelor and master's at the University of Hamburg, where she is also doing her PhD now. And today she is going to talk about her work on CMB hotspots from tachyonic instability of the Higgs potential. Julia, the stage is yours.
Yeah, thank you very much. Thanks for the introduction and also the invitation. So I will talk about CMB hotspots that come from the tachyonic instability of the standard model Higgs potential. And this work is done in collaboration with Sven Haag, Gudrid Modga-Pick, and Bibhushan Shakya. Yeah, and the starting point for this project was a paper by Bibhushan, where he looked into the standard model Higgs potential and its tachyonic instability, from which we can exponentially enhance Higgs particle production. So here you can see the potential, and at high energies, we can approximate the potential as this part, where the field appears with the power 4, which then dominates over the first part of the potential. So for low energies, we have the typical Mexican head, that's the full potential. And for high energies, we can approximate it using only the second part of the potential. And at energies around like 10 to the 11 GeV, this parameter lambda runs negative. So then we run into this negative regime, or like tachyonic regime, that you can see here on the right end of the plot. And in this tachyonic regime, the mass squared of the Higgs particles would be negative. I've written the mass here. The mass squared would be proportional to lambda. Oh, sorry, there's a square missing, lambda times h squared, and then the lambda would run negative at high energies. And then we have a negative mass squared. The equation of motion for the Higgs field you can see here. And until about 17.3 times the Hubble constant, Hubble friction causes the Higgs field to slow roll for several e-folds. And then after that, until about 3 times the square root of the Hubble constant times the Planck mass, sorry, somehow this is jumping a little, then Hubble friction becomes negligible and the Higgs field diverges quickly. And however, the infloton energy dominates over the Higgs potential energy. And in this window between these two numbers, that's where the Higgs particle production becomes important. So in this window, the Higgs mass evolves non-adiabatically and then modes with momenta k, where k is smaller than the mass of the Higgs particles, get populated with the occupation number n. And n then is equal to the Bogoliubov coefficient beta to the power 2. This usually is around order 1. And for tachyonic masses, this Bogoliubov coefficient beta gets exponentially enhanced. The enhancement factor you can see here. And then this omega is the mass squared plus the wave number k, and the mass squared in the tachyonic regime is negative, so the omega squared would be negative, and then this would be positive, this exponential. And this exponential enhancement of Higgs particle production during inflation can even win against the inflationary dilution, so that at the end of inflation, where usually the universe would be empty, we would still have Higgs particles left. And some observable effects would be gravitational waves, primordial black holes, and imprints on the CMB. And in this work, we want to concentrate on the last point, the imprints on the CMB. So how does this work? So we have the tachyonic instability, and from this we get the Higgs particle production. And then massive particles can modify the curvature perturbations And then local curvature perturbations in turn cause hotspots on the CMB, which we then could observe today. So hotspots would be localized deviations from the background temperature of the CMB. Something like this has been done in a paper by Kim et al., where you can see one of their plots here. They have looked into also a scalar particle with time-dependent mass, and they have plotted here, for example, the temperature perturbation in dependence of the time of the particle production. And this is what we want to do for our tachyonic Higgs particle. So we have done the first part. We have looked at inflation and the Higgs particle production. Now we can go on and look into how massive particles modify the curvature perturbations. And for that, we look into the action of a single particle with mass m, which can be written as you can see here. And we assume that the particles become non-relativistic right after production and can then approximate the action as you can see here. In the ADM formulation, then we can write it down as you can see here, where zeta appears, which is the, I'm just going to move this up a little, where zeta is the co-moving curvature perturbation, which is a gauge invariant quantity. And it is defined as the generalized gravitational potential, with h being the Hubble constant and phi the inflaton field. And for the following, the important part is the last part of the action where this zeta appears. And remember, this is a gauge invariant quantity. And the next steps I will only say briefly, but not explain in detail since we do not have enough time. So we would switch to conformal time and to momentum space, where k is the wave number. And then we can compute the one-point function using the in-in formalism, and then integrate over time to get the one-point function of the curvature perturbation. So here again, the Hubble constant appears, the inflaton field, eta star in this integral would be the conformal time of particle production, and then also the mass of the particle appears here. So that is the expression for the one-point function of the curvature perturbation. So we have understood how massive particles modify curvature perturbations, and we can go to the next step, how localized curvature perturbations cause hotspots on the CMB. By the way, sorry, I forgot to say in the beginning, I usually say hotspots. In general, we could also get cold spots. It depends on how large and at what time this over or under density in the early universe appears. But as we will see later for our work, for some preliminary results, we get hotspots. So usually I just refer to them as hotspots, but they could also in theory be cold. Yeah, so we start with the first order perturbation of the metric. This can be decomposed into scalar, vector, and tensor perturbations. From the tensor perturbations, for example, we would get gravitational waves. And the scalar perturbations, for example, show the response of the metric to a non-rotational distribution of matter. And this is what we care about in our work. Since also this zeta that we saw before, just 2 slides earlier, that also depends on the scalar perturbations. So, and the line element considering only the scalar perturbations can be written as you can see here, where phi is the distortion of the scale factor. B and E will be 0, since in the following we will be working in the Newtonian gauge. And then also this psi, the generalized gravitational potential appears. This is the same generalized gravitational potential that also appeared for the curvature perturbation zeta in the definition a couple slides earlier. So, and the temperature anisotropy due to curvature perturbations can be then written as you can see here. So we look at the temperature perturbation compared to the background temperature T. And here the fields psi and phi appear. Those are the ones from the line element that I also have written here just for memory in this box. This is already in Newtonian gauge. So here I have removed the fields E and B already. And then we integrate over time, and we have a visibility function here. We have tau, the optical depth, and hat would be the direction of the photons that come from the CMB. And yeah, then we would have to integrate over conformal time. However, if we use the instantaneous decoupling approximation, where we assume that all photons decouple in one instant of time, we can write the expression as you can see here, where we can replace the integral by just evaluating these at the time of decoupling. And we can then split up this equation into three parts: the Sachs-Wolf effect, the Doppler effect, which can be neglected, and the integrated Sachs-Wolf effect. So after neglecting the Doppler contribution, we can also write it as you can see here, where we factorize it in Sachs-Wolf contribution times the curvature perturbation plus the integrated Sachs-Wolf contribution times the curvature perturbation again. And the Sachs-Wolf and integrated Sachs-Wolf contributions we can get from the code class. And the curvature perturbations are just the one-point functions which we calculated a couple slides earlier. So these are known for us, and they depend on the mass of the particles. We then go to position space and evaluate at a position x0. Then we get this integral, we get some Legendre polynomials, have to sum over these, but still we have the Sachs-Wolf, integrated Sachs-Wolf contribution and the curvature perturbation here. So this is the final expression. So this is the curvature perturbation divided by the background temperature of the CMB. So now we have understood everything. We know how to get the curvature perturbations on the CMB. And how to get the CMB hotspots. And now we can look at some preliminary results. These results are just preliminary, where we are using some first rough estimates, since the exact results for the tachyonic Higgs particles are still underway. So we plan to do some lattice calculations. So while we are waiting for these results, we are using some first rough estimates. And a first estimate has shown that these tachyonic Higgs particles would collapse into micro black holes with a mass of order 1,000 kilograms, very roughly. And the lifetime of these micro black holes would be the usual black hole lifetime that depends on the mass to the power 3. So here for the first plot, we have used a constant mass of 1,000 kilograms, and which would correspond to a lifetime of 45 nanoseconds. And we have varied the time of production. So this is the conformal production time on the x-axis, and then on the y-axis, you can see the temperature perturbations in microkelvin. And as you can see in the beginning, there is not a lot happening. And then later we start to get an increase in the temperature perturbation. And this increase is mainly caused by the Hubble constant, which appeared in our calculations. Because the Hubble constant after inflation starts to change. And then for later times, this change shows up in the temperature perturbation. Another test which we have done is setting one time of production at the end of inflation and then varying the black hole mass. So we vary between 100 and 1,000 kilograms, and the lifetime of these micro black holes then changes accordingly. So here it's the other way around than in the plot before. The plot before had fixed mass and lifetime, but varying production time. And here we have fixed production time, but varying mass and lifetime. And we see the higher the mass, the higher the temperature perturbation, which is what we would naturally expect. So if we have an object with a higher mass, we assume higher curvature perturbations, which results in higher temperature deviations in the CMB. And we do see it is a very strong dependence. So we cover here orders of magnitude. So we have a very strong dependence on the mass of these micro black holes. And a last test we have done while we are waiting for the results is that we have looked into a general primordial black hole. So that due to curvature perturbations in the early universe, this black hole, the mass within the horizon would then collapse. So this happens when the wavelength of a wave number k is about the size of the horizon. And then the mass within the horizon collapses into a black hole. So that's why the mass then depends on the wave number k. And the wave number k, or the horizon size, grows with time, of course. So by changing the production time, we get a larger horizon for later productions, and then have more mass within the horizon. So here in this plot, we changed everything at the same time. Before we had the changes isolated, and here we change everything. We have shown on this x-axis the change of production time, but as I said, depending on the production time, also the mass changes, and then depending on the mass, also the lifetime changes. And we see here about the same behavior as in the plot before, because the main temperature deviations come from the effect of the mass of the particles. And an interesting area for temperature perturbations would be order 10 microkelvin, because in the paper from Kim et al., they have shown that for hotspots with temperature perturbations of around like 30 microkelvin, they can still be detected. And then larger temperature deviations would be easier to detect, of course. And for smaller temperature deviations, it would be harder to detect this. Yeah, so what remains for the future to do is to include the exact Higgs particle production. So include the results for what exactly is the mass of these micro black holes that the Higgs particles decay into. And then also, of course, we need to include a distribution of Higgs particles or micro black holes. So far, we have looked only into one hotspot. And then we also want to look into further effects, non-Gaussian effects. A colleague is going to look to the gravitational waves we can get from these tachyonic Higgses. And another interesting direction could also be looking into connections to cosmological tensions. We have not had the time yet to look into these, but some tensions that are observable in the CMB are a lack of two-point correlations, a preference for odd parity, alignment of low multipoles, a cold spot, and a preference for a larger value of the lensing parameter. And to explain those tensions, you would need some non-Gaussian effect along with some scale dependence, since most of these tensions appear at larger angular scales. And as I said, we have not done the calculation yet, but our mechanism does offer the opportunity to have non-Gaussian effects in some patches of the sky. So we would have to look if it's possible to do some connections, but this could be an interesting direction. And just to conclude, we have seen there is a possibility to produce observable signals. The results do depend on the production time, which rather becomes important for later production times. And there is a very strong dependence on the mass of the particles or micro black holes. So to see if this effect is really worth looking into, we do need the exact results. And we hope to, in the future, show you some more exact calculations. And thank you very much.